Okay, question 4. Nitration mechanism. So this is a sort of uniform question in that all nitration mechanisms are identical. It doesn't really matter what else is there. A pi bond breaks, it attacks the nitro group. So that's part A of the question, just seeing that you know how to make the electrons flow to get this to happen. Part B of the question is explaining a regiochemical strangeness that happens with halogenated benzenes that doesn't happen really with anything else. So we're going to come back to that in a moment. We start with nitric acid. And sulfuric acid. And what we have is nitric acid acting as a base in the presence of sulfuric acid because acidity is a relative term. So in this case, sulfuric is much stronger. And what we get out of that is two cations directly adjacent to each other. It doesn't get much more unfavorable than that. So very, very quickly, this is going to undo the cation problem and give us our active electrophile. So I get my NO2 cation. So at that point, I have two different possibilities that can happen. One, the alkene that gives me the ortho substitution can break and give me the ortho substitution. In doing so, I get my resonating cation. And then some friendly neighborhood base, probably water from the previous step, comes in, removes that proton, reforms the pi bond, and we're here. The other version is not that much different. So what happens then is relatively straightforward. A pi bond is going to attack the nitro. If it's this one, I get ortho. If it's this one, I get para. So I have two possibilities here. And for the moment, at least, they're equal. Ortho and para don't differ in terms of resonance stabilization of the cation. They differ in terms of what other substituents will have a problem with. These are the two resonating cations. The cations are going to resonate to the exact same spots, be stabilized or destabilized for the same reasons. By resonance. Resonance is not the answer to this question. So at that point, something, probably water from the previous step, is going to take away that hydrogen and reform the pi bond, giving us back the aromatic system. So top case gives me ortho. Bottom case gives me para. Now, in both cases, the cation can resonate next to the fluorine. So if I had taken the pi bonds and shuffled them around, I could end up, and I'll just take the bottom example for the moment, end up here. So if I resonated that down, I could end up with this. And fluorine has lone pairs, so it can resonate inward like the other halogens. The problem happens in getting things started. we can look at this slightly differently. We can look at this as a question of resonance before the electrophile attacks. I did that. Resonate that into the ring. I end up here. This is the genesis of the orthopara problem, is that I end up with essentially a negative charge, a resonating negative charge anyway, on the ortho position, and then if I keep going with that, it ends up in the para position. So those are the two positions that are activated by resonance. And this is cationic in this resonance structure. So resonance-wise, those two are both benefiting. However, inductively, this is the most electronegative element on the table, which means it is pulling with all its might on the electrons of that covalent bond, which in turn is doing the same thing here. So that is actually making this very slightly positive. As a result, it's not going to direct to the ortho position very effectively. It's going to basically have it's going to have very little nitration happen at the ortho position because it's already cationic, at least in terms of inductive effects. That's only a problem for the halogens. That's not a problem for anything else. So that problem does not exist for oxygen. For oxygen, the resonance is dominant. So the operative question for the oxygen is this. This is the resonance structure for the oxygen that we care about. It's very active at the ortho position. This group is tiny, so there's no steric issues, and its resonance is closer, and statistically there are two equal ortho positions, so ortho substitution is preferable for the resonating case of an oxygen, even a nitrogen, not for the halogens, at least not for fluorine and not for chlorine. Once we're down to bromine and iodine, they're not electronegative that much anymore. The electronegativity has dropped off as we move down the table, and so those are reasonably good at ortho substitution. Despite larger sized atoms, the ortho position is better resonance-wise because there's two of them. And so what we see is more ortho substitution happening. The fluorine, the chlorine are the problem children because of their inductive effects, the electronegativity being high enough to be a problem through the sigma bond system at the ortho position. Inductive effects don't transmit well. If you think about the difference between inductive and resonance, is the difference between calling somebody on the phone and as being the resonance version versus sticking your head out the window and screaming their name as the inductive. The inductive does not carry very far. The resonance version could carry around the world in a fraction of a second. So resonance effects are much stronger unless the inductive effect is dominant. That's only going to happen very close to the electronegative atom. This is also why I said in the previous question that a trifluoroacetate group is not going to behave the same way. It has a massive difference in electronegativity because of those fluorines, and so its behavior is a little bit different because of that.